Say drunken man is wandering around randomly in a large space. In each step, he moves one distance, north, south, east, or west, with all equal probabilities. We're choosing the coordinate 0, 0 as the initial, and then at some point in time, he's at x and y. So these steps are basically taking one step in the y-axis direction, or moving downwards or upwards, and same in the x, up, right or left. We're letting x and n and rn be his position and distance from the origin at n steps respectively. And we're also given a hint that xn is sum of random variables taking the possible values -1, 0, 1, and same for yn. Okay, and here we're asked first to think about dependence in A, and then finding covariance, and after that we're going to figure out where this drunken man is in expectation in this coordinate space. Okay, so thinking about dependence, well, first of all, let's just write out the coordinate space just to get a sense of where this drunken man might be, like so. And so what we have here is that, at some point in the space, we'll have the drunken man, be it Rn, which is xn, yn spaces. Okay, so we're going to determine first if the x and n is independent. And actually, first of all, let's just write out what x and n means here, so that we get a better sense for what that means. So let's define z. We'll say so x of n is basically a sum of random variables of z I from step 1 up to step n, where little z can take values -1, 0, and 1. Okay, and the same for yn. It's a sum from j1 to n, where we can define this random variable w moving into space, and basically w has also the possibility of being -1, 0, or 1. Okay, and so we're going to determine whether x and n are independent. Well, actually they are dependent, because imagine that we observed the probability. We say the probability here of x and n after set n is equal to 4, and we observed the drunken man just moving. The question is then, what is yn? Do we have any information about yn, little yn? Well, if this happened to be that x and n is 4 and n is 4, well, with probability 1, we know that this drunken man, basically say that he's moving to the right all the time. Well, we know that we have all information about what y is. Basically, y has to be 0, because all the steps the drunken man has taken has been moving in one direction. So yn and xn are dependent. The second part, we're asked to figure out the covariance of these two terms. So the covariance of x and yn are, by definition, the expectation of xn, yn, minus the expectation of xn times expectation of yn. Okay, so here we can observe that, and yeah, let's take this expectation here, and this will be the same expectation for this guy here. The expectation of n is the same thing as taking the expectation over the sum of random variables zi's, I equal 1 up to n. By linearity, we can just move this in to the sum, because we don't have any dependence across steps, cross movement, because they're random. And we know that the expectation of zi has to be 0, because we'll have with equal probability the unit moving in the same step left as right. So let's just write that we have n of these terms, n of expectation of zi, and zi is, as I said, sum of, let's just write it out. So there's 1/3 probability of moving to the left, and then 1/3 probability staying still, 1/3 probability of moving to the right. And this is indeed 0. Actually, there's one important thing here, is that these probabilities are not 1/3. I just recall now as I was speaking, they should actually be 1/4. 1/4. Why? Well, because if it's a zero, this unit. So say that we are at this point here. We're at this point here, and then can either move in left direction or right direction, or we stay still. But if we stay still, it means that we have information about the unit moving either up or down. So it means that in total, and these are equally likely, so we'll have 1/4 probability, right, left, and jointly 0 will have to be 2/4 probabilities. So let me just correct this. So this is 1/4, 2/4, and 1/4, and this is still 0. Okay, so this is equaling 0, and this is equaling 0. And what is this then? Well, this one is a little bit more complicated, because we have all the terms of z's and w's multiplying each other. But let's figure out what this is. So this will have to be, so let's write this down, expectation of xn, yn, and that's the same thing as the expectation of all the sums of z's and w's, and this is going to be z1, up to zn plus, so. And then we have the w1 plus up to wn, like so. Yeah, and so this in turn has to, we'll multiply in all the terms. So we'll have z1 multiplied by w1, and then the rest. So we'll have, and then the same thing with z2. Actually, this should be an n here. So we'll end up having, how many terms do we have that are of equal index? So all the ones together, all the twos together. Well, we'll have that occurring n times. So n times, I'm going to write expectation like so. I have a big expectation. So we have n times where zi is multiplied with wi. Okay, and we have, how many times do we have where the units are cross multiplied, so i's and j's? So we have zj wi. Well, that will occur n, so we'll have n minus 1 times for each j. So for each, so for example, for when j is equal to 1, so for 1, we'll have one time where it is actually the same unit, but we'll have n minus 1 times where there are different units. But we are multiplying that n times because we have n indices that we are multiplying. So this is happening n times, like so. And then by linearity, we have n minus 1, expectation of zj wi plus n expectation of zi wi. Okay, well, seems a little easier. Now this term here, when z is 1 or minus 1, then wi has to be 0, and vice versa. So when one is non-zero, the other one has to be 0. So this will always be 0. So we have expectation of 0 is just 0. So that term disappears. And we have the zj and wi's, they are independent. So across steps, we aren't seeing any there's no information flowing through. So this, we can use independence, expectation of zj times expectation of wi, but that by what we just showed here is also 0. So this whole thing becomes 0. So it means that the covariance, I mean, this guy here is 0 and these guys are 0. So we have that the covariance of xn, yn is also 0. Okay. So in the last part of this exercise, we're asked to find the expectation of Rn. Okay, and so Rn by the Pythagorean theorem will be basically we have Rn is the same as the x squared n plus y squared n, right? So Rn squared is just x squared n plus y squared n. So this we're going to use, we're going to take the expectation over this. Let's write C here, like so. And right. So we take an expectation and using linearity. So what do we have? We have the expectation of r squared n. Is going to be expectation of x squared of n plus y squared of n, like so. Okay, so the expectation of xn here and expectation of yn here, they will be the same. I mean, it doesn't matter in which direction we're moving, they have the same distribution. So we can write this whole thing as 2 expectation of xn, like so. Okay, and that in turn we can write out as the 2 expectation times the expectation of all these z terms. So we have all these z terms, z1 plus up to zn. That's the sum that we handled previously. And that in turn is just 2 times the expectation of, and this is now basically that we have the z1, well, let's call this when it's multiplied by itself, and plus the number of times, and this is basically, you can see this is the covariance, but this is the number of times, and choose 2, and that is zi zj. So when they're different, actually we shouldn't use the same index here, so we should probably just call this k, because jw is taken by the w term that we handled for the j1. Okay, so now we can use linearity, and then we figure out that this thing here is the expectation of z2i, and that's the same thing as, this is the same thing as 2 times, and we have the n. So this ends up being we have the expectation of zi zk, and this is the actually my bad, this shouldn't be a, and choose k like so, it should be just a 2, because we have those occurring 2 times here. And so the expectation of, let's start with the this term here. So what's that? Well, so this cross term here as zi and zk, they are in fact independent, right? Cross steps we have independence. So this is just expectation of zi, expectation of zk, and those we calculated earlier to be 0. So this term disappears, and we end up with this term here. This is the last term that we need to calculate, and that let's do it here. So this guy here equals, that expectation by definition is the sum over, we have I taking values -1, 0, 1. That by Lotus is, we take that times z to the power of 2, and then we figure out what the density of this z to the 2 equaling z is. That again, by definition of what we calculated up here, of the movements, of what possible movements we have, we can then take for -1 squared, that's times 1/4, that's the probability of that occurring, 0 squared, that occurs with probability 2/4, and then the 1 squared, that occurs with probability 1/4. And so what we have here is half. In fact, we can notice that the z squared I is a Bernoulli trial probability half because of this movement in space, where if you move to the left, that's 1/4, 2/4, 1/4 there, 1/4 there, and those together become it's basically indicating whether there's a movement at all. That's what the z squared term is doing here. Okay, and we are essentially done now. So we have this whole thing becoming 2 times 1/2. And right, we have, importantly, we have n of those terms. Sorry, I forgot this here. So we have n of these terms, and that's why also actually my mistake again. This should be an n squared here, but that doesn't matter for the final calculation because it ends up being a 0 there. So we have n of those expectation terms. So we have in the end this whole thing becoming n times 1/2 n, which is just n. And so that is what we were asked to find, the expectation of r squared n.